Okay, welcome back everyone. We have, in a kind of hurry, concluded with the chapter on the Kerr metric. Actually, I plan to speak more on this, but time is running short. And we have now 2 more lectures, and what I decided was that today I will talk very shortly on, well, I plan to call it astrophysics of black hole. Let me write it in this way, but it's now actually a little bit overdoing it. Actually, what I want to talk about is just the status of observations, what kind of observations we have for identifying black holes in the sky. I've already briefly talked about this in the introduction, but I think I should say a few more words now with all the background we have hopefully developed. So I think I will spend 45 minutes or so on that. And then the rest of the time I want to use on for telling you at least a little bit on the general theorems of black holes. I think the course would be very, very unsatisfactory if I hadn't ever mentioned the black hole thermodynamics, so I want to speak at least briefly about this. So I will begin with this in the second half today. Okay, but let's talk about observations a little bit. So I've already mentioned in the introduction that there is quite good circumstantial evidence for the existence of black holes, and that actually we believe that there are 2 types of black holes, which, about which we already have observations. The first class are the so-called stellar black holes, which have a few solar masses, typically at least 3. And maybe up to 30, but not more than that. And the most famous and oldest candidate for a stellar black hole is Cygnus X1. So let me talk a little bit about what we know about this thing. Well, as the name suggests, it is an object in the constellation Cygnus. That's a swan, high up in the northern sky during the summertime. You know the swan? It's this constellation. Looks like a cross, and this object this is Deneb, the brightest star in the constellation, and this object Cygnus X1 is about here. But you won't see it with a with a binocular because it's an X-ray source, as the name says, and fortunately, X-rays do not reach the Earth, right? So from an Earth-bound position, we cannot observe X-ray sources. We need satellites or rockets in order to do this. So Cygnus X1, as the name just means, it was the first X-ray source which was observed in this constellation. And actually it was detected in 1964, and it was one of the very first detection of a radio source, and it was found by a sounding rocket. A sounding rocket, that's something which is not shot into an orbit, which is just shot upwards and then it falls down after a certain time. So during its going up and then going down again, we have a couple of minutes or hours in order to do some observations, and these things were called aerobeam. So these were several sounding rockets which were launched in 1964, and where they went high enough so that they could observe X-ray sources. Actually, they did this just with the help of Geiger counters. So they had Geiger counters on board, and where the rocket was rotating, and then the counter swept over a certain stripe in the sky, and in this way, a couple of X-ray sources, not very many, were detected, and Cygnus X1 was one of the brightest. I think it is, until now, it is the brightest permanent X-ray source in the hard X-ray regime. So that's something like 100 kilo electron volt, as I say in English. So in this range, one usually doesn't give the wavelength or the frequency, one gives the corresponding energy. Yeah, you can convert from frequency into energies, well, just with with a factor h bar. So usually X-ray measurements are given, in particular the hard ones, are given in energy, in units of energy. Okay, so what did one see? Well, it was not at all clear in the beginning what it was, because these first detectors had a very, very low resolution. So it was not clear where in the sky exactly this object was situated. So one just knew about there's a strong X-ray source. That was all what one could deduce from this observation. And then a little later, the first X-ray satellite was launched. It was in 1970. Does everybody know the name of this famous first X-ray satellite? You're not old enough to... I'm sorry, Uhuru, exactly, yes. It's a Kiswahili word meaning freedom. So this was an X-ray satellite, so it was in orbit, and it did X-ray observations over a longer period, and it detected a lot of X-ray sources, I think several hundred. And it investigated closer this source Cygnus X1, which was already known. This Uhuru satellite, the instrument on board of this, I think it had a resolution of about 30 arc minutes. That's the diameter of the moon. Yeah? So if with this instrument you see a source, you know it is somewhere within a disk of the diameter of the full moon. So it's not a very high resolution. Actually, X-ray telescopes up to now have a much weaker resolution than other telescopes. So I think the best X-ray telescope we have by now is a Chandra satellite. And this is just a little bit better than an arcsecond. So that's, of course, way behind optical telescopes and even several orders of magnitude more behind radio telescopes. Okay, so one still didn't know where exactly the object was. So this, of course, meant that it wasn't clear if it was identical with some optical or radio source. Yeah? Because one didn't know exactly where it was situated. But what this satellite observed was that the radiation, the X-ray radiation coming from this source was rapidly varying. It was varying on a time scale of less than 1 second. And now if you have a variable light source, then the time scale on which it varies gives you information about the extension in space of the light source. Because if something varies in time, then, well, it's not very likely that an emission region here and an emission region there just by coincidence become brighter or weaker. So usually there's a causal correlation between them. But if there's a causal correlation between them, then light must travel from one position to the other position. It must have enough time to travel from one position to the other one within the time scale on which the thing varies. And on this observation, because it varied on a time scale of less than a second, you could already estimate that this is a fairly small object. It couldn't be bigger than something like 200,000 kilometers. This was the estimate at this time. But that's in comparison to the Sun? 700,000 is a diameter, it's a radius, actually, it's the radius of the Sun. So this is less than, 14 by 2, about 1/7 of the Sun in terms of diameter. So it's a fairly small object. So, and that's an upper bound. Yeah, it could be much smaller, that's an upper bound. It couldn't be bigger than this if it varies on this time scale. So let me write this. Let me write variation on small time scale. And this implied that it must have a diameter of less than, say, 200,000 kilometers. By now, the time is the diameter is even much better limited. But that what was seen at this time. And then luckily one observed a radio outbreak an outbreak of radio radiation, which was observed with radio telescopes. And with radio telescopes one could localize the object much better than in the X-ray. And then it gave this radio observation gave very strong evidence that the thing is associated with a particular star, which is visible in the optical. With a bright blue star, so-called O star, the spectral type, which can easily be observed in a small telescope. So it's situated here. It's a blue star, a bright blue star, and it's approximately 8th magnitude or something like that. So the weakest stars, which can just be seen with the naked eye, are 6th magnitude. Yeah? And it's a logarithmic scale. So it's 2 logarithmic steps lower than this. So this is a bright source, which can easily observed with small telescopes. And then this, I can write down the name of this star. It's a somewhat complicated thing. So one observed that it is in the neighborhood, let me write it this way, of blue star, optical star, visible with optical telescopes, which has a catalog number like that. And people, of course, started looking at this object, trying to find some information about the X-ray source from this. It's fairly obvious that the object, from the beginning, that the object itself couldn't be the X-ray source, because ordinary O stars usually don't emit strongly in the X-ray. But one thought that it might be associated with this object, not just by coincidence in the same direction in the sky. And this became certainty when the spectrum of this object was investigated, and one identified some spectral lines, and one was able to measure the redshift with fairly high precision. Yeah, so when you identify some lines, you see they are not where they are in the lab, and from that you deduce the relative velocity of the thing towards us or away from us. And what one found was that the redshift varies periodically with a period of a little bit more than 5 days, 5.5 days approximately. So the thing comes towards us, goes away from us, towards us, away from us. And this was a rhythm of 5.5 days. What does this mean? Of course, it doesn't make a motion like that. That would be very unusual. Much more natural assumption is that it rotates. Yeah? And it comes towards us, away from us, towards us, away from us. And with a period of, as I said, a little bit more than 5 days. So obviously this was one partner in a binary. Yeah? And then of course it was fairly obvious that the partner was responsible for the X-ray emission. Yeah? So what we see is a star. You see in the optical, with an optical telescope. With an X-ray telescope, we see another object. And the idea is that the two things rotate about the common center. And one thing is an ordinary star, and the other one, it is not visible in the optical, and it must be fairly small, yeah? Considerably smaller than the sun. That was at this stage already clear. And so let me write this. So redshift periodical with period, something like 5 days, 5.5 days or so. And this implies that it's a companion in a binary. And then there was another interesting observation. There were no eclipses. So this means that we don't see the thing edge on, right? If you would see it edge on, then the star would eclipse the X-ray source periodically, but this didn't happen. So obviously the orbital plane must have a certain inclination. what the exact value of the inclination, of course, was still an open question. Then quite an interesting observation was made that, well, not only the redshift varies periodically, but also the intensity of this blue star varies periodically. That's a little bit unusual, right? If an object just goes around a common barycenter with a partner, then usually you wouldn't expect the intensity to vary strongly. And the explanation, the idea people had, well, at this time already there was a suspicion in the air that this partner, this X-ray source, might be a very compact source which accretes matter from the other partner. And that this accreted matter, this matter falling onto the compact object, so that produces the X-ray emission. And well, this idea that, or this observation that variable intensity with the same period of a little bit more than 5 days. And the idea, the fairly obvious idea, is that this object is strongly deformed. Yeah? If it is a spherical ball, then it would always have the same intensity. But if it is elongated in one direction and now it rotates, then we see, at some time we see a big cross-section, and at some other time we see a smaller cross-section. This makes a variation in the intensity. So the idea is that we here have the X-ray source, which we don't see in the optical, and then this companion is a star, which is, well, I overdo it a little bit, but something like that. So elongated towards the partner. And well, when we watch from here, so here we see, it more or less circular. But in this position, we see this deformed cross-section, right? And you see, then of course, we see a much bigger surface. And so that's the idea. Well, it should be maybe perspective. In perspective, you might imagine it in this way. So the idea is that this is more or less rigidly rotating about the partner. And now the question is, what could this object be? So it must be from the period. You get some information, of course, about the orbital parameters. There's certain degeneracy. You cannot determine the orbit uniquely, all the parameters, the masses, and the inclination, and the semi-major axis, and so on. But with some redundancy, you get with some degeneracy, you get information on that. And people tried already in the 70s, and they're still doing this. They tried to make an exact model of the motion of how this thing is, of how these two things are moving. And well, an estimate of the masses, if you combine it in particular with the evolution theory of stars, which is pretty far developed. So then you can remove this degeneracy from just the orbital observations, and this clearly indicated that this bright star has a magnitude, has approximately has something like, let's say, 18 solar masses, 18, 19, 20 or so. And that the other one, the compact object, where the X-ray source is, where the X-ray radiation is produced in the neighborhood. That is, well, in earlier sources you find smaller values, but in the course of time it has always become bigger. So a couple of years ago it was 10 solar masses were defined in the literature. Now you find 15. So it's 15 solar masses in a volume which is certainly much smaller than the volume of the sun. Yeah? So it must be really a very compact object. This thing is big, by the way. This thing is big. So this is much bigger than the sun. Yeah? It has several solar radii, 20 or so, I think. So this is big. The bright one is big, but this one is very compact. And already in the early 70s, people started thinking this could be a black hole. What would be the alternatives? Well, couldn't be a white dwarf. White dwarf is a well-known final state of a star, but we know that there is a strict upper limit for the mass of white dwarfs. That's the famous Chandrasekhar limit, which won Chandrasekhar the Nobel Prize when he found it in the 1930s. He got the Nobel Prize in the 70s, I think. And this is, well, already at this time one knew that the object is much heavier than what a white dwarf could be. So 15 solar masses is much bigger than this Chandrasekhar mass, which is something like 1.3 solar masses. The other possibility would be a neutron star. Well, for neutron stars, we don't have strict upper limits for the mass. The first estimate for the upper limit of a neutron star was in this famous Tolman-Oppenheimer-Volkoff paper from 1939. They found 0.7 solar masses. But this was soon realized that other models are possible. This was too special. Well, nowadays we know for sure that there are neutron stars of up to 2 solar masses. The biggest one we have observed has a little bit more than 2 solar masses, but most people believe that that's about the upper limit. Maybe 3, but not much more than that. And as I said, there is no strict upper limit which has been derived until now. The upper limit for the mass of a neutron star depends very strongly on the internal structure of the thing, on the equation of state and on other assumptions which we make about the interior. In particular, if it is rotating, then it's very difficult to get really rigorous theoretical limits for the upper mass of a neutron star. But everything with which people have come up is in the order of, say, 3 solar masses at most. So 15 solar masses is certainly completely out of the question for a neutron star. So it can also not be a neutron star. And then, of all the objects we know, actually a black hole is the most natural, the best understood thing. There are more exotic things. Maybe you have heard about boson stars or Grava stars or things like that, which are purely hypothetical and where it's really speculative if they exist. And if they exist, they must have very peculiar properties. And it's hard to make a model how they actually can be formed. And black holes are fairly good understood. We expect them now to exist, and this is a very natural candidate now for a black hole. So one argument is just by exclusion, like Sherlock Holmes always argued, right? If all other possibilities have been excluded, then it must be the only thing which remains. That must be the truth. That's always the argument in the Sherlock Holmes stories. And along these lines, one could say this points towards a black hole. So this is by exclusion of other things. I should say there's another piece of evidence which I find quite compelling. What people have observed is that when I said the X-ray source is variable. Yeah, it varies over time and very strongly and very with big amplitude and quite irregular. And from time to time one sees what is called, what is the name, dying pulse trains, I think. Yes, dying pulse trains is the technical terms. So this is something where you observe a signal dying down, vanishing, very softly, without anything dramatical happening. And that's exactly what you would expect if there is an event horizon and the infalling matter goes over the event horizon. You would not expect something like that if an object has a surface. Then you would expect that, during the course when it falls down, of course it will emit some radiation because it's accelerated and there are charges and so on. But a strong emission would then be emitted in the moment when it hits the surface. That's what you would expect if there is a surface. And one has never observed something like that with this source. And what one has observed is this soft dying, just being shifted out by as one would explain, by an increase in redshift when the object approaches the event horizon. So this is also a strong indication that this thing has no surface. Yeah, that it is not a star with a surface, that it is something, where matter is just falling in without hitting a surface. And I've already mentioned in the introduction this bet between Stephen Hawking and Kip Thorne. This was about this object. And I think the bet was, they agreed about this soon after these discoveries in the early 70s. And Hawking said it's not a black hole, Thorne said it is a black hole. And actually Hawking paid up, I think, in the 90s. Then he said, okay, now I'm convinced the evidence is so strong that it is a black hole, now I accept it. And then he said he was convinced from the very beginning that it is a black hole. He was just doing this bet as a kind of assurance, just in case that it came out that it's not a black hole, then he wouldn't have wasted his whole life with this theory, and he had at least the consolation that he would have won the bet. That's what he said in hindsight. So this was about this object, Cygnus X1. So I would say among the stellar black holes, this is the best candidate we still have. I wouldn't say that it's proven that it is a black hole, but there's very, very strong circumstantial evidence, and most people actually believe that it is a black hole. Well, we have been talking about the shadow of a black hole, and you might ask, maybe one could observe the shadow of this thing. This would be even stronger evidence that it is a black hole, or at least an object which is so compact that the photon region is exposed. But unfortunately for these very, in comparison to the supermassive black holes, very lightweight objects, there's no chance to observe the shadow. Well, we can estimate the Schwarzschild radius of this thing. If it has 15 solar masses, so what is the Schwarzschild radius approximately? Yes, 3 times 15 is what? 45, I think. And what's the unit? Yes, 45 kilometers. And I think, I forgot to tell you about the distance. The distance of this thing is, so if we look at the Schwarzschild radius, it would be something like 15 kilometers. And now it needs the distance. The distance of this, of the bright star actually could be determined by parallax. Yeah, it's close enough so that you see a parallax. You're familiar with parallax measurements? Yeah? We are living on the Earth is moving around the Sun. This means we see distant objects at different angles in the course of 1 year. Yeah? And so, just by measuring the angular difference in the position in the sky, we can get a measure of the distance. And this star is close enough so that actually the parallax is measurable. It's only a few microarc seconds, but that's feasible in the radio. This whole system also emits in the radio range, at least from time to time. And the distance was something like 2 kiloparsecs. So what's that in comparison to the distance of the center of our galaxy? Who knows how far the center of our galaxy is away? So, order of magnitude, the radius of our galaxy. So is this much smaller or much bigger or about the same size? Well, distance of our galaxy, the center of our galaxy is 8.5 kiloparsecs away. So it's a little bit, it's 20%, 25%, something like that. So it's, not too far away, actually. And but now you see, you can imagine what's the angular measure you would expect here. Okay, actually the shadow is bigger than these 15 kilometers seen at a distance of 2 kiloparsecs, because first, as I always emphasize, the shadow is not determined by the horizon, it's determined by the photon region, which is bigger than the horizon, and also because of light bending. Light is bent, And this means that the angle is actually bigger than it would be if you just do a Euclidean calculation. But for the order of magnitude, if you are interested in the order of magnitude, you can just take this distance divided by this and look up the tangent of this, and then you get the order of magnitude of the shadow. And this is, of course, this is tiny. Yeah, this is something like, what is it? 10 to the minus 9 arc seconds. Something like 10 to the minus 9 arc seconds. Yeah. So this is, for the foreseeable future, this is absolutely out of the question that we will ever observe this. So the shadow of a stellar black hole is not observable. So we need other circumstantial evidence. So as I said, we observe these X-ray signals from matter falling into the black hole. We also receive signals from matter orbiting the black hole. From the periods, you can get some information. There's some indication that one sees what is called quasi-periodic oscillations. So the matter going in such an accretion disk, this will not be exactly in the disk. It will have a slight motion also in the theta direction. And there are resonances between the theta motion and the R motion. And they are they are determined in a characteristic way by the parameters of the object at the center. So if we would see this in an idealized way, then we could even deduce angular momentum and the mass of the central object. So all this points towards the black hole. Probably, about the spin, this is still, I think it's still a matter of debate. There was a paper a couple of years ago where they came to the conclusion that the thing is almost not rotating at all, where it is almost static. And then came other papers with other observations from these X-ray, this kind of X-ray observations I just mentioned, which point in the opposite direction, that it's very close to an extremal black hole. I think this question is still open. I'm not sure if this has been settled by now. So one doesn't know how fast this object is rotating. Also, if we could see the shadow, this would clarify this immediately, right? Because if the shadow is circular, then it's not rotating. If it's not circular, then it is rotating. So it would be very nice if we could see the shadow, but as I said, this is out of the question. So I think that's about the situation with Cygnus X1. And this is the most famous candidate for a stellar black hole, but by far not the only one. We have more than a dozen good candidates. From time to time, a candidate drops out, and it turns out that it is not a black hole, that it is a neutron star. This happened for one of the very promising candidates, which was considered in the literature for many years as a good candidate for a black hole. A couple of years, people found out that it is a neutron star. Yeah, there were very clear evidence that actually it is a neutron star. But there are, at least a dozen. If you are a little bit generous with the word good candidates, then it's even more. And they are typically, candidates, they typically have masses, and they are all in binaries. Yeah, they are all observed in this way, that they are binaries, and you see the partner, you observe, you get the information about the orbit from the partner, and then you deduce the parameters of the X-ray source, or the object at the center of the X-ray emission, candidates with masses. And what you find is that they are between 3 solar masses. These are the lightest ones which we have, and they go up to something like 30 solar masses. So Cygnus X1 is a typical example, more or less in the middle. So that's about the situation with the stellar black holes. So very strong evidence that there are objects which are neither white dwarfs nor neutron stars, so they are either black holes or something more exotic. That's the status of the stellar black holes. Now let's talk about the supermassive black holes. The best candidate, the most famous candidate, and the closest candidate is, of course, a thing which is called Sagittarius A star. That's the center of our galaxy. Yeah.
Just a short question to the normal black hole. You said that the upper limit is about 30 solar masses. Is this just from observation?
From observation. From observation. Yeah.
The theoretical limit.
Theoretically, it could be bigger. It could be bigger. Actually, from a theoretical point of view, just considering general laws of nature, there's no reason why we should only have these stellar black holes and the supermassive black holes, the ones with a few solar masses and the ones with billions of solar masses, millions or billions of solar masses. There could be something in between, with hundreds or thousands or something like that. And people are speculating about this. So these are the so-called intermediate black holes. But the evidence for their existence is fairly thin. So there's not really good observational material that they actually exist. So many people speculate that they might exist at the center of globular clusters. As you know, the galaxies are typically surrounded by a halo of globular clusters. So these are these things which in the sky look more or less circular, like a fuzzy circular spot in the sky. And there's a certain conjecture that they might harbor in their center intermediate black holes. But there's no really strong evidence for this. So here, for the supermassive black holes, the best candidate is Sagittarius A star. Actually, one shouldn't say the black hole candidate is Sagittarius A star. Sagittarius A star is a radio source, and this radio source is associated with a black hole candidate. But one shouldn't identify the two things. In the same way as one shouldn't say here the X-ray source is the black hole. Yeah? Well, I should have mentioned this before. The black hole itself cannot emit anything. Yeah? There cannot be anything being emitted from inside the black hole, then it wouldn't be a black hole. So if we see something, then it's always emitted in the neighborhood of the black hole. It comes from matter which is falling into the black hole or falling towards the black hole or something like that. And in the same sense, Sagittarius A star is a radio source which is produced in the neighborhood of the black hole candidate, but one shouldn't identify it. So first I should say, why do we observe the center of our galaxy not in the optical, but in the radio? Well, in the optical we don't see anything. Yeah, there's so much dust, we cannot see the interior, the innermost region of our galaxy. We cannot see anything there. So you know, in the sky, this is in the direction of the constellation Sagittarius, der Schütze in German. So it's in the northern sky we can observe it during the summertime, but it's fairly close to the horizon, so it's not really nicely observable from Bremen, for instance. Yeah, if you go to more southern regions, then you can view it much better.
But for the phantom.
It makes it a little bit better, but not much. Okay, so when you watch this central area of our galaxy, even with a small telescope, it's very impressive. Yeah, it's much brighter than the rest of the sky, and you already see in comparatively small telescopes you see a lot of dust. These black regions where dust prohibits us from looking through. And in the immediate neighborhood of the center of our galaxy, we don't see anything because of this dust in the optical. But the dust is more or less transparent already in the infrared and also in the radio. And also on the other side in the X-ray. So we can get information from the inner part of our galaxy, in particular with radio telescopes, and that's what people did already in, when was it, 74 was this radio source discovered. So again, this is something where people very soon realize that it is contained in a comparatively small region. So the region which actually emits the radiation must be fairly small. And how small it must be, this became clear later, when these famous observations of infrared stars in the neighborhood of this object began. This was in the 90s, in the early 90s. Now with infrared telescopes, actually observation of stars near Sagittarius A star in the infrared. And this was since, I think, 1992 began the observation. So this was done with two big telescopes, or is done until now with two big telescopes. One is the VLT, the Very Large Telescope in Chile, and the other one is the Keck on Hawaii. So the people who are doing the observations with VLT, they are German. That's the Munich group, the group headed by Reinhard Genzel. And the people who do the observations with the Keck, this is an American group led by Andrea Gees. And so they are working independently from each other with different telescopes, and the nice thing is they produce results which are very well fitting together. Yeah? So they confirm each other. Well, there are certain numerical differences from time to time, but by and large they come to the same conclusion. What do they observe? So they observe stars in the neighborhood of, so here is this radio source, this rather compact radio source, and then we observe stars, and they are fairly, they don't need much time for a full revolution. So there's one star, they are called S something, these stars. And the one which is denoted as 2 is the most famous one, because it was the first who made a full revolution. Actually, the orbit is more eccentric. I showed it draw like that. So this one made a revolution in 15 years. Yeah, 15 years for one revolution. So one had a full orbit. I think the observations began in 1992. So in 2007 or something like that, a full orbit was found, and there are other ones. Yeah, there are quite a lot of these stars which are observed, and by analyzing the orbits, we get very precise values for the mass of this object. Yeah? So these are certainly test particles. These are stars which are the mass is much lower than the mass of the object in the center, so we can treat them as test particles. So this would be, if the non-relativistic approximation, the Newtonian approximation is valid, then this would just be Kepler ellipses. And actually what one observes is they are Kepler ellipses to an incredibly high accuracy. So, and what one finds from this observation is that the mass of the object in the center of the gravitational center, which produces these orbits, that this is something like, they are now already discussing the digits after the decimal dot. So I think the usually given number is 4.3 times 10 to the 6 solar masses. And this corresponds to a Schwarzschild radius of about, I have to multiply this with 3, let's say roughly 12 times 10 to the 6 kilometers. And we know how far the center of our galaxy is away from us. So from observing these orbits, we can also get information about the semi-major axis of this, the semi-major axis is this, of these objects. And this is much bigger than this. It's about 1,000 Schwarzschild radii. For all these stars, it's in the order of magnitude of 1,000 Schwarzschild radii. So this tells us that the Newtonian approximation is still very well valid. So, and as I said, they are Kepler ellipses with a very high precision. This means that actually it is not an extended source which extends over these orbits so that they would go through this material, but that the source is really inside. It's completely inside. So this gives then a limit for the size of the object. And from other information, actually, the size which one gets is much better. So just from the observation of these stars, we find that it must be smaller than 1,000 Schwarzschild radius, something like that. So if you make a model for this, where the thing is bigger than 1,000 Schwarzschild radii, then it would be in contradiction with observations. And Yeah, one also observes, one was looking for, in analogy to the situation with the stellar black holes, one was looking for, for indications that there's a surface. So one was looking for signals where matter is falling onto a surface, and then it emits radiation at the moment when it hits the surface. And people looked for this very, very intensively. And they never found anything like that. So the upper limits for radiation really coming from the surface is incredibly small. So it can be, I think it's 0.4% of the total radiation or something like that, which is totally unbelievable if it's really an object with a surface where matter is falling onto in the usual way. So you need a very, very peculiar mechanism which makes the radiation being produced before the surface is hit. Yeah? Practically everything, practically every emission would have to take place before the surface is hit. And it's very difficult to come up with accretion models of this kind. So let me write no evidence for existence of a surface. And this is, of course, a big obstacle for making models other than black holes. So, of course, for such an object with such a mass, of course, we don't have to talk about white dwarfs or neutron stars. That's, of course, absolutely ridiculous. So, from the very beginning, it was clear it's either a black hole or it's something more exotic. And the model must be such that it doesn't have a surface on which matter is really falling. That makes it very difficult to make alternative models. And for this object, we are actually hoping to see the shadow. There are now fairly expensive and intensive attempts underway to observing these shadows. Is this the shadow? There are two projects. To observe the shadow. One is an Event Horizon telescope. That's an US-American led project, and the other one is a black hole cam. This is led by two Germans and an Italian who lives in Germany, so it's largely a German project. And these two groups, they are collaborating, so they are not fighting against each other. They are partly using the same telescopes actually. And these are VLBI observations. So the plan is to link together telescopes distributed all over the Earth. And if you do this, then you get very, very good resolutions. The resolution would be comparable to what you have with one telescope, where the diameter is just corresponding to the distance of these telescopes, roughly. So you can reach resolutions of something like micro arc seconds. So with VLBI, we are now in the range of micro arc seconds observation, and that's what we need. So the expected diameter, we have calculated it. You remember, for this kind of black holes, for this value of the mass, if it would be a Schwarzschild black hole, then it would be circular, and the expected diameter would be something like 53 or 54 micro arc seconds. And this is feasible already now with VLBI. So one tries to make these observations in the far infrared, so near the border to the radio regime. So that's something like around 1 millimeter. So that's a different range from where these observations are made. They are made in the near infrared, so something like micrometer, wavelengths of micrometers. That's what one calls near-infrared, NIR abbreviated. So these observations with the VLT and the instruments which are linked to the VLT, they are in this range, and they are good for observing these stars. They are not good for observing the shadow, because in this range the scattering would be too strong. So it's good for observing stars which are fairly far away from the center. But if you really want to zoom in towards the center of the object, then you should use a different frequency range. And actually, when this project started, there were not very many telescopes which could work in this sub-millimeter regime. Now a very big one was built. It's ALMA, the telescope in Chile, which will be one of the main players in this game for looking for the shadow. And there are a couple of other telescopes which are able to observe in this range, and so people are hoping to see the shadow in a couple of years.
Is this 53 micro-arc seconds, or is it expected?
Yes, yeah.
But is it diameter or resolution? I mean, is it
That's a diameter. That's a calculated diameter. We did the calculation actually in one of the exercises for a Schwarzschild black hole of this mass. And okay, now I understand. So that's what one has to resolve, and that's already feasible with telescopes now. So the resolution is not the problem. So people expect that the scattering is a bigger problem. Yeah, that everything will be washed out by scattering. That will be the bigger problem. Actually, I said that this radio source Sagittarius A star is fairly compact, and actually it has been localized already to within a radius of 30-something micro-arc seconds, 37 or something like that. Hey, wait a minute, what is that? The shadow is expected to be 53 micro-arc seconds, and the radio source, which has something to do with matter around the black hole, this is smaller than this. Isn't that nonsense? No, actually it is not. Actually it is what one expected. Do you have an idea why this emitting region from which we actually receive the radio radiation is smaller than the thing itself, the central thing itself? Well, where will the radiation come from? Well, one possibility would be that it is radially infalling matter, but that's actually not the most likely case. The most likely case is that it is going around the center. And then it will come towards us on one side, then it will be Doppler enhanced. It will go away from us on the other side, it will be Doppler weakened. So what we see is essentially the thing which comes towards us, which is Doppler enhanced. So this is a bright spot going around the center, and that's what we actually observe as a radio source. Yeah? So that's a very natural interpretation. And there was one paper in Nature actually where the radio astronomers said they have found evidence that the barycenter of the thing, so what we have from these observations, where really the center of gravity is situated, that this doesn't coincide with the center of the radio source. And that's exactly what one observes, what one expects. One expects the radio source to be a little bit offset. Yeah? So everything fits perfectly well together. So the only thing which is still missing is the actual observation. And we are hoping for this, to see it in a couple of years. And then also the question will be settled if the thing is rotating or if it is not rotating. Yeah? So if it is circular, then it is not rotating. If the shadow is circular, then it's not rotating. If it's not circular, then it is rotating. And if we observe the shadow, then I should again emphasize, this is not an ultimate proof that it is a black hole. There could be also other objects which cast a shadow. For the shadow, the photon region is the essential thing. Yeah? In the Schwarzschild case, R equals 3m, not R equals 2m, R equals 3m. And in the Kerr case, it's this thing with a crescent-shaped cross-section. This is a relevant thing for the shadow. You could think of an object which is not a black hole, which is actually a regular object in the center, but where this object is so small that it still disposes the photon region to an outside observer. It is smaller than the photon region, but bigger than the horizon. Something like that is called an ultra-compact star. And the difficult thing is you would have to make a model where the surface is not visible of this thing. Yeah? It must be something like a perfectly absorbing surface. Yeah? Not something which is hit by infalling matter, which is then radiating. That's what makes it difficult. And another thing is stability. To build models of ultra-compact stars is not too difficult, but practically everything which has been tried until now turned out to be unstable. So if you perturb it a little bit, then it becomes something completely different. And that's not what we expect from the thing in the center of our galaxy. It seems to be perfect. It seems to be fairly stable over many years. So it should. It's difficult to make a model other than a black hole. So as I said, the black hole is the most natural explanation for everything. You can come up with something exotic if you try really hard, but at the time, for the time being, a black hole is the most, the simplest, the most obvious explanation. There's not much going on around the center of our galaxy, unfortunately. People were hoping for seeing dramatic events when matter is falling into the black hole. This happens very rarely. Well, there was some event early this year, but in the X-ray there was a certain eruption when some matter fell into the central object, but this is really rare. So the object at the center of our galaxy is much more quiet, much more silent than what we see in other galaxies. There are these so-called active galactic nuclei, so the center of other galaxies where a lot of firework is going on, where an enormous energy is released when matter comes towards the center. Something like that is almost never happening in the center of our galaxy. There was this famous cloud, G2, maybe you have heard about this, which was observed, I think it was discovered 2 or 3 years ago. It was an object moving similar to these stars, going around the center of the galaxy. But some indication was pointing towards the thing that this is not a star, but rather a gas cloud. A gas cloud, which would then be distributed over the whole orbit by the gravitational forces of the central object. And people were hoping that this would fall into the black hole and then produce an X-ray firework. And so this was even in ordinary newspapers, not in scientific journals. In ordinary newspapers, you could read articles about this, that people were waiting for watching a black hole at lunch. So this was the wording you could find in some newspapers, but nothing like that happened. The thing moved around and nothing dramatically happened. And now people believe that probably it does have a star at the center, which keeps the whole thing together. So it isn't really disrupted in the way as people were hoping for. So it has now gone through its pericenter to the point closest to the center, and nothing has happened until now, and now the chances are not very high that something will happen now. So this was a big disappointment in the last years. Okay, so that's about the status for the supermassive black hole, if it is one in the center of our galaxy. And of course there are many other candidates. Also the Andromeda galaxy is a very good candidate. We are fairly convinced that there's a black hole in the center of the Andromeda galaxy, even bigger than in the center of our galaxy, by a fairly big factor bigger actually. There is a famous M87, maybe you have heard about this. This is the one with a big jet. People are speculating that it might even be 2 black holes which are orbiting each other at the center. So something like that would happen if 2 galaxies collide. If 2 galaxies with black holes at the center will collide, what we would expect is that the 2 black holes form a binary black hole. So that's what people are speculating about in the case of M87. This is close enough so that also for this object the shadow might be observable. It's something like 15 microarc seconds, I think, diameter for M87. That it's still within the range of VLBI observations for the foreseeable future. So M87 is next to Sagittarius A star, the best candidate for a supermassive black hole. So that's the status. So we have a number of candidates, and some of them much heavier than the thing at the center of our galaxy. So let me continue here. So candidates between, as in the case of the object in the center of our galaxy, that's a few million solar masses, and this goes up to 10 to the 11 solar masses. So for M87, it's something like 10 to the 10, or maybe even a little bit more than that. So we expect that some of them are really very massive. This is still also in the case of Sagittarius A star. This is still small in comparison to the mass of the whole galaxy. Yeah? So you shouldn't have the idea that the majority of the mass is in this black hole in the center. No, that's not. It's a comparatively small fraction. Okay, so I think that's. Oh my goodness! I was hoping to make this in 45 minutes, but. Of course, I didn't manage. So this was a very brief overview of the status of observations, and I tried to point out that we most urgently wait for the observations of the shadow. At least in my view, this would be the most intriguing thing which we can expect for the foreseeable future, and which might happen soon. Okay, but then let me go back to theory again. So let me talk a little bit about black hole theorems. I think I should say a few words about this. And the first group of theorems or statements I want to talk about a little bit is what goes under the name of black hole thermodynamics. So this is associated with two names, the names of Jakob Bekenstein and of Stephen Hawking. Of course, also with contributions from others, but I think these two were the most important person in this game. Actually, Bekenstein did this as a PhD student. He was a PhD student of John Wheeler in the United States, and he had this rather crazy idea that there's a certain analogy between the theory of black holes and thermodynamics. And he was able to convince John Wheeler actually to work on this. Most other people he had talked to about said this is absolute nonsense. Yeah? But Wheeler took this seriously. And then it made Bekenstein famous. He's now a professor in Israel, and has done in later years several other important contributions to gravitational physics and also other fundamental theories. And Hawking, of course, was also strongly involved in this. In particular, he proved the version which we nowadays usually give for the analog of the second law. He has this law that the entropy always is growing. This is the area theorem, which was essentially proven by Hawking. Okay, what's all this about? It's about an analogy a formal analogy between black holes and thermodynamics. So we associate certain quantities which are associated with black holes with quantities which are associated which we know from thermodynamics, and we observe that there are similar laws, that there are analogs of the laws of thermodynamics, the first law and the second law, also the zeros law, and that we can find them again in the theory of black holes. And in order to understand this, we have to talk a little bit about what quantities actually are relevant for the black hole. So for a black hole, we have, of course, a mass. We usually, when we're talking about the Kerr black hole, we use this parameter little m, which has a unit of a length, but which contains the same information as a mass. So it was just, so let me write this. So the mass m, and we express it usually in terms of this parameter m. Then we have the angular momentum. This was J, and we express this usually in terms of this parameter little a, which is essentially the specific angular momentum, the angular momentum divided by the mass. And then to make this also into a length, one puts the factor c here. So the little m contains the same information as the big M. The little a contains the same information as the j if I know the mass. Yeah? And then we have also already talked about the area of the horizon. This will play a role in this for these theorems. And actually we have calculated this for a Kerr black hole. If you remember, I can write it down for a Kerr black hole. We have done this in one of the worksheets. And if we know it for Kerr, then of course we also have the special case for Schwarzschild. Yes, 8 pi m. R plus is the radius. I'm talking about the outer horizon. Yeah, we have a rotating black hole. We have two horizons, R plus and R minus. A Kerr black hole. Then this is the outer horizon, the event horizon for an outside observer. And we will need some other quantity, which I have not yet introduced, which I will have to introduce now. This is the so-called surface gravity, and about this I have to talk a little bit in a little bit more detail. Oops. Actually, whereas just the word surface gravity, that's something very familiar from Newtonian theory. We use this word for the acceleration on the surface of a body. So if we are here standing on the Earth, then the acceleration which a body will experience if we let it go, then that's what we will call the surface gravity. How big is it here on Earth? The surface gravity, the acceleration which a body undergoes on the surface of the Earth?
9.8.
Yeah, what? The units are important. 9.8 is correct, but what?
Kilogram meter over second.
Meter per second square, yeah. Something like 9.8 meter per second square. That's the surface gravity here on Earth. Now people try to introduce something similar for black holes, and there you observe an obstacle. Actually, we have the surface gravity here on Earth. We could put it in this way. It is if I multiply it with the mass of the thing, then I get a force, right? Mass times acceleration is a force, and this is a force I have to support in order to keep this in place. Yeah, just in order to balance the gravitational attraction. So it's a force which I need up to the factor m. It's a force which I need in order to keep the mass at rest. And this thing we have already calculated for the Schwarzschild spacetime. So we have calculated what is the force which is necessary to keep an object at a certain radius coordinate r in the Schwarzschild spacetime at rest. This means on the t-line. This was one of our, I think, the fourth worksheet or something like that. Yes, fourth worksheet. Acceleration necessary to keep, it's a test mass. It's something which doesn't distort the gravitational field. To keep test mass at rest in Schwarzschild. And what we found was this, the acceleration. So this is something like that, right? Actually, if I, so that's the 4 velocity, the u, yeah? So I have my world line, I parameterize it with proper time, and then the tangent vector is this u, so it's normalized to minus c squared. And the covariant derivative of u in direction of u, that would be what one calls the acceleration. And in the case of Schwarzschild, if I want to keep the particle at rest, it has only an r component. That's intuitively fairly clear, right? The acceleration is pointing in the radial direction. And the AR we have calculated, and we found this is c squared Schwarzschild radius over 2 rho squared square root 1 minus rs. I dropped this index. We are at the radius r now, yeah? In the worksheet we wrote r0 for the radius where we were positioned. And now you see, if we want to define the surface gravity of a black hole just by applying this value on the surface of the black hole, this means on the horizon, then we see that it doesn't work. If I insert r equal rs, the whole thing becomes infinite. Yeah? So according to this construction, the surface gravity would be infinite. And actually, in a strict sense, I would say the surface gravity of a black hole is infinite, of a Schwarzschild black hole. Yeah, if you define it just in an analogous way to, as we are used, as we do it for a star, for an object with a surface, then, and we now replace the surface by the horizon, then actually the surface gravity is infinite. Nonetheless, one can introduce something meaningful, which one then calls the surface gravity of a black hole, by multiplying this with a redshift factor. So this, I said u corresponds to the parameterization with proper time. Yeah? So this derivative here is the derivative with respect to proper time. So we calculate the acceleration with respect to proper time. If I supply a redshift factor, this means I convert proper time into coordinate time. Coordinate time is proper time for an observer far outside, at big radii. Yeah? So we would express the whole thing not by looking at what an observer actually at the place of the mass would have to do in order to keep it in place. We would ask, what an observer at infinity would have to do. Yeah, it's a little bit difficult to imagine how he should practically do this, because he would need some sort of connection with this body, which is far away from him, in order to provide the necessary acceleration. But if you are able to imagine that this can be done, then you could say we now calculate the surface gravity in terms of acceleration for an observer at infinity. Yeah, not for an observer who is at the position where our mass is situated, but we supply a redshift factor d tau by dt. So what one calls define the surface gravity of a Schwarzschild black hole. We will then generalize this. And this is usually denoted kappa. It's an acceleration. Yeah, it has the dimension of an acceleration. And it is just this quantity AR. This factor here for the this factor in front of the basis vector of the oh, by the way, sorry, I made a mistake here. This is not a unit vector, right? Sorry. What I've written here is actually It's the length of this vector. Yeah? If this were a unit vector, then the length of this vector would be just the AR. But because this is not a unit vector, that's not true. So this is the wrong symbol. Maybe I should put it like that. Yeah, that's what I meant. And what we calculated. It's really the magnitude of the acceleration. So then we have this here, and I now supply this factor d tau by dt. Tau is proper time, and t is coordinate time. Yeah, this factor is 1 if we are far away from the center. But if we are close to the horizon, then it's not at all 1. Actually, it's, what is it? d tau by dt, if you just look at the Schwarzschild metric, just write on the left-hand side d tau squared, and then you write everything out on the right-hand side. You see this is just the square root 1 minus rs over r. That's d tau by dt. Yeah? So let me write this here. So we have d tau squared if I have an and all the other ones are 0. Yeah, because I'm on a t line. I keep my particle on a t line. I keep it at rest. Then I have this relation, right? Just from reading. Oh, c squared is missing here. Oops. Tau should have the unit of a time, right? So that's it, and that's what I've inserted here. And the acceleration we had calculated, so this is c squared rs 2r squared square root 1 minus rs over r. And this corrected acceleration, corrected by this redshift factor, this stays now very nicely finite. If I send r to rs, then I get, well actually, sorry, this is a kappa, the limit is a kappa. C squared rs over 2 rs squared, and so I have the rs in the denominator, and that's what one calls kappa. That's the surface gravity. So it's not so immediately interpreted, because I have to I need some interpretation for this factor here, which is necessary in order to make the whole thing finite. But apart from this fact that you have to correct from proper time to coordinate time, apart from this fact, it gives you a measure for the strength of the gravitational field, yeah, for the acceleration which you need in order to keep a particle in place. Well, now this calculation doesn't tell you immediately how you could generalize this to more complicated black holes, Kerr black holes, or maybe even other black holes. But there is another way of introducing the same quantity, an equivalent way of defining this quantity. Oh, this is spelled with an E in English. Of defining kappa. And this will then actually be a definition which we can generalize to other black holes. And this makes use of the killing vector field which generates the horizon. So the general definition of the surface gravity of a black hole will be given in terms of the killing vector field which generates the horizon. And for that, well, if we want to evaluate things on the horizon, not in the sense of a limit, but if we really want to go to the horizon and evaluate the things directly there, then we should use a coordinate system which is regular on the horizon. Yeah, and for this reason I will now use Eddington-Finkelstein coordinates. So I could use any coordinate system which is regular on the horizon. Eddington-Finkelstein is the most convenient ones, and let me just remind you how the metric looked like. It was minus 1 minus rs over r, c squared dt prime squared. Yeah, that's the Eddington-Finkelstein time, ingoing Eddington-Finkelstein. And then comes the mixed term. Eddington-Finkelstein has a cross term, dt prime dr, and the rest, which is actually not interesting, rs over r dr square plus the angular part. And so in this coordinates, the killing vector field which generates the horizon is d by dt prime. Yeah? You see the coefficients are independent of t prime, so it's a killing vector field. And if this this becomes light-like on the horizon, yeah. So we have the killing vector field, which I denote k now, which is, well, let's for dimensional reason, let's divide by c, d by dt prime. So then this expression, gkk, the quantity which tells us what causal character k has, this becomes 0 on the horizon, right? So this is just gkk, or let me write minus gkk. Then I have 1 over c squared. This kills this c squared, so I have just 1 minus rs over r. Yeah. And so you see this is 0 on the horizon. So on the horizon k is light-like. This is bigger than 0 if I'm outside of the horizon. So this means k is time-like outside of the horizon, and inside the horizon k is space-like. And this is a scalar function, right? Let me call this phi. And my claim is that the kappa, which I have defined here for the Schwarzschild spacetime. So my claim is that I can construct the kappa in the following way. I take the phi and calculate the gradient. Yeah? Derivative with respect to the mu's coordinates. That's the coordinate expression for the gradient of phi. Well, what's that? That's a function which on the horizon, the function phi is on the horizon light-like. If I have a function, so phi equal constants on the horizon is a light-like surface. Now, if I take the gradient, usually I used to the fact that the gradient is perpendicular to the surface, right? So it points out of the surface. But if you have a light-like surface, then the light-like vector is perpendicular to itself, and the gradient is tangent. Yeah? So on a light-like surface, which is written in the form phi equal constant, on this surface the gradient is tangent. Yeah, that's a property of light-like. Of a light-like vector field, and this means that this must be proportional to this killing vector field k and the covariant component. So this means to this thing, g mu nu. And there's a factor in front of this. And my claim is that the factor in front of this is determined by the kappa. Up to a numerical factor, it's just the kappa. What's the factor? 2 kappa over c squared. And, well, on the horizon, at r equal rs. And that's something which can be done, this construction can be done whenever my horizon is generated by a killing vector field. So that's a general procedure how to introduce a kappa. This was special for Schwarzschild, a very particular calculation for Schwarzschild. I should prove this. So let me see if I manage to do this today. So obviously the phi depends only on r. So I have dt prime phi is 0, and dr, no, this has no prime. Dr phi, this is everywhere 0, in particular at r equal rs. And if I take the derivative with respect to r, I get minus rs over r squared. And if I take this at r equal rs, I get minus 1 over rs. Okay? Now let's calculate the right-hand side. The right-hand side, so I need gt prime, t prime, kt prime, plus, yeah, that's it already, because k has only a t prime component. Yeah?
Shouldn't this be plus? Because we have this defined as 1 minus r is over r.
Oh yes, thank you, you're right, yes. There was a minus sign. Yeah, that's why I wrote this to the other side, so that this becomes positive outside, right? Okay, so what is this? G t prime, I can read from the metric. This is minus 1 minus rs over r c squared, and this is just 1. No, 1 over c, sorry, 1 over c. So, and if I do this, I get 0, right? I get 0. Is that true? Yes, it's true, of course. I want to have a 0. And G, what else do I need? GR, T prime, K T prime. The mixed term, that's the only other one which gives something different from 0. CRS over R. That's a 1, no, 1 over C. At R equal RS, this is 1. And now let's see if this is true. So this is 0. Is this really the same as 2 kappa over C squared times 0? Yes, I think that's true, right? This is 0 from u equal t prime, and from u equal t prime, I get this here, which is also 0. And the other equation that I have 1 over rs. It is really 2 kappa over c squared times 1. This would be equivalent to kappa is c squared over 2 rs, and I hope that's it. C squared over 2 rs. Yes. So I have proven that my claim is indeed correct. So the kappa, which we introduced first for the Schwarzschild spacetime in this way, can be rewritten, it can be reintroduced, or can be equivalently introduced by this equation. Yeah? And the nice thing is that this can be generalized. And this is actually the general definition of a surface gravity of a black hole. It works for every black hole where the horizon is generated by a killing vector field. These are, one then says it's a killing horizon. Yeah, so this expresses the fact that the whole thing is, in a certain sense, time independent. So this is not adequate for time-dependent black holes. Yeah, black holes in the process of collapsing. That's not feasible for them. But for stationary objects where everything has settled down, so the thing is now a black hole. It may rotate, but when it rotates stationary. Then we still have such a killing vector field, and then we can use this definition. Oh, I should mention that there's a normalization problem. I have written here a factor 1 over c. I could have written something else, some other factor in front of it. Would still be a killing vector field, right? If I just multiply it with a factor, this would mean that I multiply the coordinate with a factor. And if the metric doesn't depend on the coordinate without the factor, then it doesn't depend on the coordinate with a factor. Yeah? So this certainly preserves the property of being a killing vector field, multiplication with a constant factor. You see that this definition actually is sensitive to a constant factor, because this goes quadratic and this goes linear in K. So I have to fix this freedom, and I do this by requiring that it goes to 1 for r going to infinity. If I'm far away from the center, then I want to have my function phi, which is defined in terms of k, approaching 1. Then everything is unique. So this fixes the freedom of a constant. Okay, I'm afraid I have to stop here. So I will then next time discuss the surface gravity of the Kerr spacetime. And then I will briefly summarize the laws of black hole thermodynamics. So to give away the punchline, the area of the horizon will correspond to the entropy, and the surface gravity will correspond to the temperature. Yeah? So these are the two most important quantities for this black hole thermodynamics analogy. Okay, so I was hoping that I could do more today, but time is already out. So see you on Friday.